get out of the way. Okay, look at, say, yeet as loud as you can.
Yeet. That's actually how loud I can actually do it.
Oh, do it one more time.
Yeet.
P is for parasympathetic system. S is sensory memory. Y is for Johann Bein. Yay, studying youth counseling here in psychology.
Hey guys. Let me hear. Start up a new unit. Today we are going to be learning about sensation and perception. This is a introduction to the ideas. We're going to be going over a lot of the terminology and whatnot. There's a Vsauce thing attached to this. It talks a lot about in the way we interpret stuff. So watch that because he's way more entertaining than I am and has better production values because he has the time and the knowledge on how to do that. So let's go over this. So sensation, perception. So sensation is the stuff that comes, is the process by which we receive information from the environment. So let's make this kind of bigger. There we go. So stuff comes in us from the environment. You see a picture of an orange bird. These things come into your face, or you hear my voice and you hear these things, and the sensation is the process by which you receive information from the environment. So, what type of information? Well, we've got stimuluses. Stimulus. So stimulus is just a thing that excites something. So we have light. Light is, you have a wave or photons, depending on how you want to look at it. Here's an eyeball. It's a weird looking eye, but there's an eye. And it comes in, and the eyeball gets it, and we'll do that. So the sensation, the stimulus is light. Here with sound, you've got sound waves. See if I can draw an ear. It looks like a weird potato. So sound waves look like this. Light waves can also look like photons, depending on how we do this. It's coming out of some guy's mouth. And we hear that. You smell chemicals. R for smell, here's a nose, and taste, there's a tongue. Those are chemicals. So what actually is happening with smells and tastes is kind of cool, are the chemicals coming in and it's attaching to a receptor in your mouth or in your nasal cavity, and that chemical then sends a signal to your brain. So what's the chemical? Well, it's generally found in the thing that you're tasting. So if you can smell poo, it's because there's the chemicals of poo basically in the air. When you eat a pepper, the reason that it burns is there's a thing called capsaicin on there, and it is a chemical. And the way that the atoms are arranged, they overload every taste bud that you have, and so when you eat something that's spicy, it's basically a flavor overload, which is why it's so tasty. Pressure, temperature, and pain, that's your sense of touch. And we'll also go with orientation and balance. So inside your ear, for example, you've got liquid, and I don't know, I'm not an expert on this, but your inner ear helps you to balance stuff. And so it keeps your perception, and so like if you spin around, it puts the fluid and whatnot that's inside there out of place, and it helps you don't have balance. This is why you can close your eyes and be able to stand up. It's also why you can close your eyes and be able to like touch your nose and stuff. Why you can like, it's your orientation. So with stimulation comes in, this tells us stuff, whether it's the balance of the stuff in the ears, whether it's light, whether it's sound. These things come into us, and that's a stimulus. And this can be in tons and tons and tons and tons of forms. So we can have a physical stimulus. A physical stimulus is a thing that you could touch, basically. Air is a physical stimulus. Vibrations are a physical stimulus. They move things. That's what sound is. Gases, which have smells oftentimes or can push on you. Chemicals, as I said. Or pressures. These are all pressures, and whatnot. Those are all physical, environmental stimuluses. But we have a pretty limited range on this. Human beings have like a really crappy sense of hearing. We can hear things, but to 20,000 hertz, we can't hear. Dogs can hear that. That's what a dog whistle is generally at, about 20,000 hertz. And what's weird is you get older, that goes away a little bit. An older person, you can use what's called a teenager whistle. And if a person is older, I can kind of hear some of this stuff still, but my dad cannot at all. And if you take this thing and you blow into it, you guys will probably be able to hear it because you're young, and it will annoy the crap out of you, but we won't be able to hear it. I can kind of hear that, but 10 more years I won't be able to. So your senses change. The light spectrum, we see a very narrow band of light. So like here's the light spectrum. Visible light is this itty bitty teeny tiny band like right here. Now luckily most of the light from the sun is in this band, but you've got like gamma rays and x-rays up here, and you got radio waves down here, and we can just see this teeny tiny band in between. Right here and right here are ultraviolet and infrared. Snakes, pit vipers can sense infrared. And what is it? A few animals can sense ultraviolet. I think maybe scorpions. I'm not 100% sure on that. I can't remember off the top of my head. Some animals can sense ultraviolet. Really cool thing that happened. You can make. This was a few years ago, but they were in the process of figuring out how to make bionic eyes, and they were testing it out on rats. And theoretically, you could get the eye of a bionic eye to be able to sense things outside of the normal light spectrum. And rats have really crappy sight. They have way worse sight than we do. And so they gave the rats like this bionic eye, and then it looked like the test seemed to indicate that they could see infrared. So there is a chance that we could create an eyeball that could see infrared and ultraviolet and other parts of the electromagnetic spectrum, and I think that's really cool. There's a part of me that wants to have a bionic eye so I can see heat. It'd be like a superpower that's also probably really annoying. So there are those limits in there. Here are some things that our body are really sensitive to. Number one, light. Through vision. So I just talked about it's part of the electromagnetic spectrum, and there's kind of three parts to it. For part one, I'll use the same things, is intensity. And we experience this as brightness. So there's a part of our eye, and we'll talk about this a little bit more in a later one when we're talking about like the parts of the eyeball that transmit and figure out brightness, how bright a thing is. Then there's wavelength. This is like in lumens. Wavelength. So wavelength is the space in between. So light goes at the same speed however you go. So this point of light goes to this point of light at the same speed always. The wavelength is how far we have in between these things. So how far do I have in between here? So radio waves are big. They might be meters across. Gamma rays are minuscule. They're still bigger than atoms, but they're like so teeny tiny. And the more you have in there, the more powerful it is. So red is a different wavelength than purple is, and you probably know that. That's hue. And 3 is complexity. So this is how much of a thing there is. So you look at a thing and how blue is it? How green is it? Is it just this thing, or are there other things around inside of it? With wavelength, this is a really interesting thing, and I'll talk about this more later, but our eyeballs are designed to see 3 colors, and then we combine them all together. We have cones, and they see different types of things. Different animals have different amounts of things. There are some birds that have 4. We have 3. Dogs have 2. Some birds have 4. And mantis shrimp, I think, have 11. It's some insane number. They can see colors that we can't even imagine would exist. If I can find it, I'll link one day to a really, really, really interesting article on mantis eyeballs. It's so cool. All right, sound. Sound is pressure waves. Pressure waves. And once again, we have intensity, same idea. We experience this through this loudness. We measured in decibels. Frequency, this is pitch. Now, you guys have probably heard of, so this is a higher pitch thing, that is a lower pitch thing. As the wave is coming at you, this is the Doppler effect. And as it's coming closer, the wavelengths are squished, makes a higher pitch, and when it goes away, it is lower pitched as they get pulled away. Waveform. Okay, so if you look at, you ever do that thing, you've seen it, and you get a waveform and it looks kind of like this. That is the sound and the notes in it. What's a way to describe timbre? Let's just look up the definition of timbre. And that'll help us. The character quality of a musical sound or voice as distinct from its pitch or intensity. So, it's kind of like the tone of a thing. So, you can have one that's really clean, or you can have one that's really, really messy, and different waveforms equal into different sounds. If you listen to audio equipment a lot, you'll see these different types of things. And if there's a lot of stuff there, it's really messy, there's a lot of background stuff, and if it's really clear, then they'll be out there. Like, a harmonic is really clear. A dissonant note is not clear at all. The wave function looks all funky. Alright. Now these things can work in together, but this is kind of how we perceive sound. So, what are the steps in perception? First off, there's a thing called transduction. Transduction. And so this is converting energy to of a stimulus to a neural activity. So whenever some sort of physical stimulus comes and touches you or causes something, it's transferring energy of some sort. A chemical thing is transferring energy. It's some sort of chemical thing is happening and it's transferring a amount of electricity, or a pressure wave makes sense, pushes you. Sound is transferring energy, light is transferring energy, and that comes in, and then your neurons, your sensory stuff and your neurons translate that thing, that wavelength or whatever, into something your brain can process. So it's like when the Wi-Fi in your house comes in, it's some sort of wave, some sort of energy, it comes into the Wi-Fi router, and then the processors in the computer turn that into a thing that you can see, and now you can look at me and get stuff off the internet and watch memes. Even though in the air it's just a form of energy. And so that becomes a neural pattern. And that's just, so you can look at the stimulation thing. We've talked about how that looks in like EEGs, when you put on the fancy helmet and then they measure your brain and then it looks like this and you get brainwaves. Those are neural patterns. And transduction can be affected by our experiences, such as through adaptation or a constant level of stimulus. Okay, so this is kind of a cool thing. So when a new stimulus comes in, let's pretend that I'm drawing a neural pattern. This is called adaptation. And when a new one comes in, it's really intense. But as we experience it more, the neural pattern decreases. This is why when you go into a place and it smells really bad, eventually you go nose blind, because it goes down. And your body goes, oh, new thing. Ah, okay, pay attention. Oh, it's not killing me. Okay. And then it goes down. It's also why your friend's house smells weird and your house doesn't smell weird, but your house smells weird to everybody else. Everybody's house smells weird. Yeah. Okay. Perception is the process of selecting and identifying information from the environment. Okay. So this is where things get wacky. So things start coming in. So the perception is our interpretation. Watch a lot of the Vsauce thing here. This is for the Vsauce. Now, you could stop this and watch the Vsauce stuff, and you'll get some stuff. So I'm going to go over this I'm going to try to go through this fairly briefly, and he'll give you more stuff. So, perception equals interpretation. So in comes red light. Boom. Red light. It goes into my eyeball. And that goes to my brain. And my brain then interprets it. That is my perception of it. And the way I interpret this is not necessarily the same way that everybody else does this, which is weird. We both would recognize red as red. Red comes in unless you're colorblind. So let's take blue. We both recognize blue or something. This is blue, or this is a cow, or this is this thing. But exactly the way our brains interpret that thing, this feels fluffy. What fluffy means, while we can agree, isn't necessarily like if I went in your brain and experienced the way that you felt fluffy, I might not recognize it. I might go, what is all of this? This is crazy, because our brains are interpreting it and doing it in different ways. So sensation, as I said here, is the existence of, so sensation equals the stimulus, or the existence of a stimulus. There has to be a stimulus there. It's there. There's some sort of sensation that comes in. You get it, and you get it, and it comes in. But now you have to make something out of it. And the perception is what is that stimulus. Here's a waveform, sound wave comes into your ear, and you go, and you hear it. That exists, and it's going to exist, but then you perceive it, and that's your brain going, that's the sound of a G chord or something like that. Now, how do we do this? Why do we do this? How does this work? There's a couple different processes for this. One would be bottom-up processes. So this is, they involve identifying a stimulus by analyzing the information available in the external stimulus. So a new thing comes in, and we analyze the stuff in there. You can kind of think of this as, I've never come across this before, and so I'm going to put it together. So here comes a new thing, a new sound, a new sensation. And it comes in, and we go, okay, we have this. This is a sound wave. It sounds weird, whatever. And now I'm going to interpret it into something. Then there's top-down, which is the one that I'm going to pay more attention to. And this is based off of experience. So sensations come in. Our experiences through our lives then help us to interpret this thing. This one generally starts with the low brain, what's called the low brain. So here's your brain right back here where you perceive things, is where you do this. Over here, your higher brain, and so we start with this, when our hippocampus, which is right there. And in our limbic system, we bring that in there, and this is where we're interpreting it into an emotional thing, or we're attaching it to something else, or we go, okay, that's music, or this is this, or this is this, and we base these things off of our experiences, and it helps us to perceive what we expect to see, because you're bringing in a lot of stuff, and it messes with you. So, here's an experiment. go find a food. And then change, like, get a food, and then this works really well with like a candy. You get a candy that's red, but you make it taste like something that's blue, or vice versa. I think I've told you about the time when my brother-in-law made clear root beer, and it made me sick. I couldn't. It messed with my brain because I wanted it to taste like Sprite or like water, but it tasted like root beer, and it was just wrong, and I didn't know what to do, and so my brain got confused. That's a result of top-down processing. I have two contrasting expectations coming. I have contrasting information. Comes in, the bottom down stuff's taking it, going, what's this? And my top down's like, oh look, Sprite. And then they don't meld, and I go, oh no, that's weird. It's also why we can misinterpret things a lot. We expect something to sound some way. We expect somebody to say something. We expect something to happen in a particular way. And then something happens, and it's not that, but we still might perceive that. A lot of biases work this way. Top-down process allow for perceptual judgments and biases to start influencing how we process information stimuli. So this leads to biases, and that's because we have to process information quickly. We need to take information in and go like, okay, thing, so I don't die. But that also makes it so we automatically make a perception and a decision on things before we even really can think about it, because our brain took this top-down processing, oh, we have this stuff, and interprets this way, and we might interpret things completely different. It's one of the reasons why you can see the same, two people can see the exact same thing happening and interpret it in a completely different way and see different things happening, because their experiences are different in their life, and they're experiencing and expecting and have biases towards different types of things. Also, one of the reasons why if you listen to a certain type of music a lot, you are able to tell between genres and styles within that music, while a person who doesn't has a hard time with that. I've listened to a ton of metal in my life. I can tell the difference between lots of different genres, and a lot of people just go, oh, that's noise. All right. Now we have psychophysics, which sounds like a fake thing. But it's not. It's kind of about, it involves math. And it is the relationship between physical energy and psychological experiences. So it's, that's a stupid picture. So here's a lot of energy, and here is your experience, there's you, and it's the functional relationship. How much of this affects this, and how does this affect this? So what I want you to do, if you can, right now, is do a little test. I got a candle right here. If you have a candle, this will work really, really, really well. I can't really do this with the way that lights in a room work. But take a second, and if you can, take a candle or a flashlight or something and go into a room or be in the room that you're in. Keep the lights on, turn the flashlight on, take a note of how dark or how light it is in there. Okay, you got that. Then turn off everything and turn that thing back on. What you will notice, I'll wait for a second, is what? Mr. Lemon! The candle was so much brighter in the dark. Yes, it was. But the candle actually wasn't brighter in the dark. The candle gave off the exact same amount of light, both times. But your perception of it is different. This is called absolute, this is related to psychophysics. We've done this a lot, where you can hear a really quiet sound when the room is quiet, but if it's loud, it's hard to hear anything, so you keep turning up the volume. Yeah. So, what we have here is thresholds. So thresholds are kind of limits. You can think of them as limits. This is how far a thing can go. So the idea of an absolute threshold, absolute one, is where we can detect a stimulus 50% of the time. This is kind of the statistical basis for, oh, I can actually detect this. So this is as far down as you go. So during this time, if you can hear a thing 50% of the time, then you are at the absolute threshold of where you can perceive this from. So, yeah, think of sounds. think of a sound, and if you could hear that sound more than 50% of the time, you're above the absolute threshold. If you can hear that sound, perceive that sound less than half the time, then it's going to be you're at the absolute threshold. And that's just the way math works. So given a particular stimulus, the minimum stimulation needed for detection. So yeah, this is how much you need in order to notice a thing. So notice. So here's a person, and they're like, "Hi, I'm here," and somebody's over here whispering. Small person, they're whispering, and as they whisper louder and louder and louder and louder and louder and louder and louder, the moment at which this person can start perceiving this over half the time, that's the absolute threshold. Hearing tests. If you've ever had a hearing test, those are what those are. Then there's the difference threshold. Now this is so this is where we can reliably do it above this. This is yeah, I'm gonna go past a little bit because we don't need to know that. Signal detection theory. So let's go to signal detection. Signal detection. So this is the theory suggests how individuals are able to detect the minimal stimulus among other background stimuli. This may influence how individuals make a decision in a specific situation. So what's interesting is we are kind of attuned to get particular sounds. A person can detect, like, if you take a penguin, and so there's these penguins, they live on this island in South Georgia, Jordan or Georgia, one of the two. It's just north of Antarctica, and there's like 2 million penguins on this island. And every single day, one of the parents will go out, get food, and then it has to come back and find the child. There's like millions of child, and they can hear each other out of all of those things. They can hear the specific call of their kid, and they find them and feed them, and they do that every day. That is signal detection theory. The idea that we are designed to be able to find particular signals as we get adapted and tuned to them. Now for the last thing we're going to talk about today is receptor sensitivity. Sorry. Receptor sensitivity. So a receptor is just the thing that your eyeball, ear, there's a hand, the things that are getting the sensation, so you can turn into a neural pathway, go into your brain, and then be translated. So one of these ideas is sensory adaptation. This can change. This can change, and I talked about this earlier. What I can hear, my range of hearing is lower than yours. My dad's is lower than his. What you can see changes over time. What you can smell changes over time. Babies are really crappy at seeing. They have really low receptor receptivity when they're first born, and then you get better. Babies see everything as blurry and like black and white. Babies are not good at seeing different colors. By the way, if and when you ever have children, and you have like those mobile things that go in circles, make it out of black and white stuff. Don't make it out of lots of colors, because the baby that's going to look at that, that's the things that they're going to be able to see, and that's actually going to help them to develop their eyesight better. So do that. So decline in receptor activity when stimuli are unchanging. Noticing if okay, so that's over a long time, but there's also the short term. Short term. So this is when we have something coming into us a lot. So you notice a sound when you go into a room and you go away. You notice a smell when you go into a room. We talked about that earlier. So that's called sensory adaptation. We adapt to a thing, and that if you look at the neural pathway, so it looks like this, and then it kind of decreases and becomes less of a thing. And habituation or adaptation. This sensory adaptation is kind of just a thing you do, and then it goes to habituation. And this changes the way in which your brain interprets it in the long run. So this is due to repeated exposures. Hold on for a second. Lemon, do a jump cut right here. I'm gonna go get myself some hot sauce. Okay, these are Takis. This is what I'm talking about with habituation and adaptation. So, Takis have capsaicin in them, which makes them spicy. This is habanero hot sauce, made in Texas. First ingredient, second ingredient or so is habaneros. Now, the spiciest hot sauce, but this is probably 10 times hotter than a jalapeno. So, this is what happens when you are exposed to a particular stimulation a lot. When you eat spicy food, it stimulates your taste buds. That sends a neural signal to your brain. Your brain then interprets that as pain. But if you eat a lot of spicy food all of the time, eventually you will adapt to it. Your brain signals will change and it will not be as intense. Here is habanero hot sauce on the Taki. I spilled hot sauce on my keyboard. You. Alright. So that's probably the equivalent. I feel it. It's not a big deal to me. That's the only way that Takis can even be spicy to me. It's because I eat a lot of spicy food. And that is called habituation or adaptation. The decline in response to a stimulus due to repeated presentations of the stimulus. And this, if you were to look at my neurons, these are the death nuts. I'm going to eat these sometime this week because I'm stupid. This is the hottest one's 13 million Scovilles. That's beyond anything I've ever eaten before. I will feel this one. This will have a large wave function on my body. But not as large if you don't eat a lot of spicy food. This barely registers. But if I were to eat this, but if like you don't eat hot sauce and you ate this, you'd have problems. We all do that. We all have something that's like that. You have a thing that comes in, you get used to it. And you don't have as much. That's called habituation. Okay, that's all we're going to go over today. We're going to go over vision, audition, or hearing, and what you see in a little more depth. Next time, there's the optical illusion thing. Do that. If you do get motion sickness or you're feeling weird, stop. I don't want you to get hurt. But it is kind of a cool thing. Anyway, look that up. Watch the Vsauce thing, and then reply back to this with your questions, your things you found interesting, and your your summary. I'm going to try to, hopefully I've got things under control enough that I can reply back to those things better than I have been, and answer some of the questions. I'm going to try to answer at least one question for everybody. I've been kind of overwhelmed lately. Alright, miss you guys. Wish you would come to the chat so I could answer questions.